Hello! Welcome to our machine learning presentation. We are Group 9 and we will be presenting a multilayer perceptron neural network with an adaptive learning algorithm for thyroid disease diagnosis in the Internet of Medical Things. These are our group members. The content outline includes introduction, proposed method, results, discussion, and conclusion. Let's get started. Internet of Medical Things (IOMT) systems analyze various data sources, such as imaging results and laboratory findings. The objective of this study is to improve the accuracy of diagnosing thyroid disease within the artificial neural network (ANN) connected to the Internet of Medical Things (IOMT) systems. In medical systems, artificial neural network (ANN) is an important machine learning method in medical diagnostics, with the ability to analyze examination results and medical image reports to aid in diagnosis. In this study, multilayer perceptron (MMLP) uses several artificial neural networks working together, in which each neural network is trained separately. Once all the networks are trained, they each make predictions on new data. The predictions from all the networks are combined to produce a final result. To provide better understanding, here is the analog of the explanation. Neurons in MLPs represent the students. Each neuron performs simple calculations. Layers of neurons solve parts of the problem and pass results to the next layer. Final output is the combined solution. The principle of MLP starts with forward propagation, which means that the data flows through the network from input to output, through input layer, hidden layer, and output layer. Next, backpropagation of ANN is used to minimize the error by adjusting the weights and biases of the network. The error is propagated back through the network, starting from the output layer to the input layer. However, challenges such as slow convergence and local minima persist in IOMT applications. To address these challenges, this study design proposes MMLP neural network approach that utilizes backpropagation error and implements an adaptive learning rate algorithm to expedite the convergence rate. This paper includes a summary of the application of the MMLP neural network in categorizing and diagnosing 3 types of thyroid diseases, enhancing classification accuracy, utilizing adaptive learning for improved performance, and achieving superior results compared to prior research. The proposed methods consist of the details of dataset preparation, feature selection, feature scaling, neural network classifier, the purposed multiple MLP, MMLP, and adaptive learning rate. An adaptive learning rate is utilized, whereby the learning rate value is adjusted in each epoch. Firstly, the thyroid disease dataset obtained from the UCI machine learning repository contains information on 7,200 patients, with 21 variables for each person. The key focus is determining a patient's thyroid function, categorized as normal, hyperthyroidism, or hypothyroidism. The dataset has the majority of patients having hypothyroidism with the data of 6,666 out of 7,200 patients, followed by hyperthyroidism and normal thyroid function. In this study, the process of feature selection is employed to choose the most relevant data points that positively impact classification precision while eliminating unrelated variables. Methods such as Pearson's correlation, symmetrical uncertainty, 1R classifier, and relief attribute evaluation are applied in this selection process. A score is calculated for each attribute based on its rank in each method. A threshold value is established through experimentation to select the most impactful data points. Eventually, 12 features, green, were chosen based on Pearson's correlation as it yielded the best results and aligned with known risk factors for thyroid disease. Feature scaling is crucial for data preparation. In the left image here, without scaling, feature x1 is much greater than x2. This causes elongated contours and a zigzagging optimization path, leading to slower convergence. On the right, scaling is applied, standardizing features to have a mean of 0 and a standard deviation of 1. This creates circular contours and a direct optimization path, improving convergence speed. Next is the neural network classifier. The model structure includes an input layer, a discrete intermediate layer with complex nodes, and an output layer. Specific activation functions are used in the intermediate and output layers to help the network learn complex patterns. However, there are also risks. First, overfitting occurs when the model relies too much on training data and fails to generalize to new data. Second, underfitting happens when the model can't capture underlying patterns, leading to reduced accuracy. Balancing the number of intermediate nodes is crucial for achieving precision and generalizability, ensuring the model performs well on both training and new data. Next, this diagram illustrates multiple MLP networks that work in parallel. We can see that starting from the data input here, information is fed into multiple MLP networks simultaneously, such as MLP1, MLP2, and so on. The parallel structure prevents overspecialization in training data, and each network processes the data independently, learning different aspects or features. Using multiple MLP networks improves the model's ability to make accurate predictions on new data, achieves more robust and accurate classification. The adaptive learning rate addresses issues with the learning rate by using a step-based approach. This approach adjusts the rate based on performance at each epoch, ensuring optimal learning throughout the training process. When there are decreases in performance, the learning rate is increased by a constant value to boost learning speed. Conversely, when there are improvements, the learning rate is decreased to fine-tune and stabilize the learning. This method optimizes the learning rate dynamically, leading to more stable and effective learning. At the onset, this table presents the results comparing percentage accuracy, mean squared error, MSE, and R value between the MMLP, improved backpropagation, and standard backpropagation, BP, methods across different datasets. The MMLP method achieved exceptional results with the highest overall accuracy of 99% and the lowest MSE of 0.0108. In contrast, the standard BP method exhibited lower accuracy at 94.4% and a higher MSE of 0.0357. Notably, MMLP outperformed standard BP by improving accuracy by 4.6%, increasing the R value by 0.06, and reducing the MSE by 0.0249. These results underscore the superior fitting and overall performance of the MMLP approach, highlighting significant advancements in accuracy and error reduction. Next, the figure illustrates the CPU time comparison between the two methods. The standard BP requires 114 seconds of CPU time to complete 3,000 epochs, whereas the improved BP takes only 18 seconds for 818 epochs. The improved backpropagation algorithm, with its adaptive learning rate, speeds up convergence, significantly saving CPU time and reducing the number of epochs needed. This accelerated training enables a more comprehensive evaluation of models, leading to better results. Additionally, resources are allocated more efficiently, requiring less computational power. Receiver operating characteristic, or ROC curves, are essential for evaluating performance, as accuracy alone is not sufficient. On the left, we see the ROC curve for the improved BP, while on the right is the ROC curve for the standard BP. The ROC curve for the improved BP leans more towards the top left corner, indicating a higher true positive rate and a lower false positive rate compared to the standard BP. The improved BP demonstrates higher accuracy across all classes, including normal functioning, hyperthyroidism, and hypothyroidism, which also signifies better performance and more reliable predictions. The study underscores the significant benefits of employing an MMLP neural network with an adaptive learning algorithm for diagnosing thyroid diseases. This ensemble approach effectively addresses the challenge of overfitting commonly encountered during neural network training, enhances generalization, and excels in performance when presented with new data. The study identifies a set of 6 networks that demonstrate the highest accuracy percentage of 99%. The adaptive learning rate algorithm plays a crucial role in enhancing training efficiency. By dynamically adjusting the learning rate, the algorithm ensures faster convergence and avoids the trap in local minima, which can hinder the training process. This adaptive mechanism is particularly beneficial in medical diagnostics, where timely and accurate results are critical. Comparative analysis with other studies in the field confirms the superiority of the proposed method, achieving a remarkable accuracy rate of 99%, outperforming previous methodologies ranging from 94.71% to 98.5%. In conclusion, the proposed method achieves a remarkable accuracy rate of 99%, which not only significantly enhances diagnostic accuracy but also reduces the overall mean squared error, making it a valuable tool in medical information systems within the IOMT framework. The network configuration is quite advanced, employing 6 networks integrated with adaptive learning algorithms. This setup not only reaches an impressive accuracy rate but also ensures faster convergence when compared to traditional methods, and it addresses overfitting concerns effectively. Looking forward, the study identifies several future research directions, including further optimization of convergence methods to ensure efficient error function minimization and tackling challenges associated with local minima in IOMT environments. Additionally, formal methods will be explored through mathematical modeling to evaluate the effectiveness of the proposed approach. These are all our references. That's all from us. Thank you.